Okay, in this video we're going to talk a little bit about fundamental and derived units, our dimensions of space and time that we use in association with these units, and a little bit about conversion. Our system is the Système International. That's a system of units that we're using that you've encountered before, no doubt. And most frequently we use the meter, kilogram, and second units together, sometimes referred to as the MKS. And there they are in purple, orange, and blue. They represent the three most fundamental aspects of the universe, or three most fundamental dimensions of the universe: length, mass, and time. There are four more that we will see on the next slide, but we want to make sure we remember our metric prefixes and the associated abbreviations and powers of 10 that associate with each one. So our base unit of length is the meter, boxed in green. That's the base unit. 10 to the 0 means I have 1, the unit, and that's my meter of length. It's good to know up to about 10 to the 9 and 10 to the negative 9, that kind of range of prefixes. And so here they are. The kilometer we see frequently and may use in problems. Mega and giga not so much, but that's what 10 to the 6 and 10 to the 9 are. We often see the centimeter, 10 to the minus 2, cm, 10 to the minus 3, the millimeter, mm, 10 to the minus 6, the micrometer or micrometer, that's mu m, the Greek letter mu, and then we have 10 to the negative 9, the nanometer or nanometer, nm. As far as mass goes, the kilogram, the 10 to the third power there, kg, is actually the base unit, not the gram. Veritasium's channel on YouTube has a nice little historical backstory of where that base unit comes from. It's the only one that's still measured by a physical thing, a platinum iridium cylinder, though in recent years there's been talk and attempts to try and get it away from that. Every other base unit is defined by a laboratory procedure or process, with the exception of the kilogram, which is still a thing. 10 to the 0, the gram, is not our base unit, though often you hear the CGS, or centimeter gram second, acronym or abbreviation for when using those three units in tandem. As far as powers-wise, we may use the kilogram, gram, and milligram in class. In labs, anything other than that is not so frequent, but those are abbreviations and powers. Well, time-wise, the second is the base unit. 10 to the 0 is 1 second, and we sometimes see milliseconds and microseconds. We'll see how precise we can be with our slow-motion capture cameras this year. MKS there, boxed in our green, and CGS indicates our centimeter gram seconds, underlined in red. We have the corresponding dimensions in orange now. Length corresponds to the meter, mass to the kilogram, and time to the second. Other than those first three dimensions of the universe, length, mass, and time, we have four others. So we'll list what those are just because we need to know them. The first semester will only really deal with length, mass, and time, and some of their derived units. And we know what their corresponding base units are. There they are. We also have temperature, which is measured in Kelvin, and we have the amount of substance, which you've seen in chemistry, of course. That's the mole. Otherwise, we also have the electric current, measured in the ampere as the unit, and luminous intensity, its unit is the candela. Okay, and there are their associated abbreviations next to them. Dimensions in black, units in colors, and their abbreviations in the parentheses. We also have derived units. Other than the 7 fundamental units and their dimensions, the only other things we have are derived from them. So velocity is one example. Change in position divided by change in time. That's a length dimension divided by time dimension, and those units, if we're using the base units, are meters per second. So you see the colors are different. We've combined dimensions, and so we have a derived unit. Force is another example. The unit is the Newton, but the Newton itself is made up of fundamental units, and those fundamental units are the kilogram, the meter, and the second. So the equivalent to 1 Newton is 1 kilogram meter per second squared. There are a couple different ways that we'll probably want to be able to do conversions. One is just by using our exponents or powers of 10 method. That's very convenient given the metric system. We only really have to multiply or divide by 10 a certain number of times when we are changing between units. Frequently we'll see some measurement that has an amount there boxed in blue. The unit I just threw an AB as abbreviation for some sort of unit in red, and often some direction. If it is a vector quantity, it needs to have a direction. We'll say more about scalars and vectors this week, but we could have a direction that might be in radians or degrees, or maybe with a plus or minus at the front, or a north or south, but those could also be described using a degree measurement, such as compasses do. So let's do an example. We say we have some amount of kilograms that we need to change into micrograms. We can write down our amount there, as I did in black, and then remember what the power of that unit's prefix means. So kilo is 1,000, so it's 10 to the 3 grams, and micro is 10 to the minus 6 grams, and x might be the number that you say we're solving for if we're saying how many micrograms are there in 1.825 kilograms. I can solve for x by dividing both sides by 10 to the minus 6 grams, and if we remember our exponents rules for dividing, we know that we should take the exponent and subtract it from the exponent, or subtract the denominator's exponent from the numerator's exponent, so we have 10 to the 3, 3 minus negative 6 will give us 10 to the 9. So I'll have 1.825 times 10 to the 9, my grams cancel out, and that's the value, the magnitude of the number that will precede my microgram unit. I can move over my decimal point. That's often what we do. We say, okay, in the metric system, we're just moving our decimal point over, or we can keep it like I did and just use the convenience of scientific notation. So 1.825 times 10 to the 9 micrograms is how many micrograms are in 1.825 kilograms. The factor label method is another popular method and very convenient for doing unit conversions. Let's do the same example again with kilograms to micrograms. I can write out my value as I've done, and keeping everything separate as a fraction can help me organize what I'm doing. So I start with 1.825 as a value and kilograms over 1, and I'm asking what is 1 kilogram equal to that I know of, and I write that out as a fraction. 1,000 grams is equal to 1 kilogram, and 100 milligrams is equal to 1 gram, and 1,000 micrograms is equal to 1 milligram. And because I've written out all of these fractions that are equal to 1, this fraction, this fraction, this fraction are all equal to 1, I haven't actually changed the value of the quantity I have. I've simply changed the units. Okay, so we can multiply that through and see what it looks like. Those can be written as powers of 10, which makes it nice and easy. I add all those 3's up there because when I multiply, I add my exponents, and I get again 1.825 times 10 to the 9 micrograms. You can notice in purple I've crossed out all of my units, and I've drawn my fractions such that I have the units that I want to cancel, such as my kilograms here and kilograms here, upstairs and downstairs respectively, so that they do cancel out. Continuing on, I could take another example that's fairly straightforward, like convert 100 meters to centimeters, and I would end up with 10,000 centimeters. I know I have 100 centimeters in every meter, so I just multiply by 10 squared, or 100, and I get 10,000 centimeters. Now, this is not the case if I were to ask you this. Change 100 meters squared to centimeters squared. Well, that's not equal to 10,000 centimeters squared. So sometimes factor label method using our fractions can help keep us straight when we're dealing with some squared or cubed units for area or volume, for instance. So here, say I have, just like before, 100 over 1 times meters squared over 1. That's originally what I'm starting with, the 100 square meters. And you can see if I multiply it just by my 100 centimeters, which are equal to 1 meter, in that third fraction down there, well, my meters squared don't cancel out with my meters on the bottom. I'm still left with 1 order of meters upstairs if I do that. So I actually need to multiply by another 100 centimeters divided by 1 meter. Again, just like before, these fractions here, this one and this one, they're both equal to 1, because 100 centimeters over 1 meter, that fraction is equal to 1, because it takes 100 centimeters to make 1 meter. So because I'm multiplying by 1, I'm not actually changing the quantity in its amount, I'm just changing its unit. So now that I have 2 meters downstairs, they're going to cancel out with the 2 meters upstairs. but that also means I'm multiplying by another factor of 100 upstairs. So there we go with my exponents, just to keep myself straight and nice and clean. 2 plus 2 plus 2 is 6, so I have 10 to the 6 centimeters squared over 1. My meters have canceled out upstairs and downstairs, and I have centimeters squared, which is what I should have if I'm going for area. And so that's, if I move my decimal point over, I would actually have to move it over 4 times, not just 2. So 10 to the 6 centimeters squared is how many centimeters, square centimeters it takes to fill up 100 square meters. Another helpful, useful way reason for using the factor label method is when we have outside of the metric system some sort of strange conversion, like how many seconds are in 1 year. I'm just going to pause this for a second. I've asked how many seconds are in 1 year, and I've set up a bunch of fractions that, again, all of the fractions that follow 1 year are equal to 1. So I'm not actually changing the amount of time, I'm just changing the number of units that are equal to 1 year. And so I ask, okay, 1 year, how many days are in a year? 365.25. Then my third fraction up there, how many hours are in a day? That's equal to 1. 24 hours is equal to 1 day. Then how many hours or how many minutes are in 1 hour? And how many seconds are in 1 minute? And you'll notice how I've done in green, I've strike out all of those units that cancel. I'll multiply all of those fractions across, and I'll end up with seconds over 1. So that's what I'm looking for, how many seconds. My years are gone. I've used those fractions to convert to seconds, and now I'm just multiplying through. So there I have in orange for consistency, the multiplication of my units using scientific notation. And then if I pop it in my calculator, you'll see in black just below, I have that that straight value with all of those digits floated. I like to do the scientific notation. It's a little less nerve-wracking to see it written in scientific notation for me. Another example, change 40 meters to inches. I happen to know that 1 meter is approximately 3.281 feet. That's a convenient conversion factor to know. We can often visualize or imagine things in feet because we deal with that a lot in the West, so it's a good conversion factor to know. So there I've done it again. I've written up only 2 fractions I need in addition to my 40 meters over 1 there to get into inches, and you can see the multiplication through with the scientific notation, or if I just put that in my calculator, I'll get 1,574.8 or so inches. So, what we do need to know, we need to know our 7 fundamental dimensions and their corresponding units. Okay, we need to be aware of our metric prefixes, what powers they are associated with. So kilo is 10 to the third or 1,000 meters, and know which base units correspond to which dimension. So I need, especially in the first semester, to know that my meters, kilograms, and seconds are my base units, and what the prefixes are, and how to convert to different powers or prefixes within the metric system. Know how to convert within and between systems of measurements. So you don't need to memorize conversion factors, but you do need to be able to go between imperial and metric system, for example, like we did with that last one of meters to inches. Alright, that's all for this video. We'll have another one coming up soon on dimensional analysis, and then scalars and vectors, and we begin talking about one-dimensional kinematics this week.